Okay. So y'all are going to be in the uber elite now, the 0.2 or 0.1% of people who know that Gaussian is a software package, not just a statistical term. So these are all original memes, so like, share, and subscribe. Okay. So yeah, we're going to be talking about building molecules in Gaussian today and learning what Gaussian's doing under the hood. Okay. So we'll practice a little bit, but you're going to get a lot of practice some practice in the lab. So in Gaussian, we use GausView to interface with the software Gaussian. So let me close that. So back in my day, we had Gaussian where you had to actually make a text file for the input. So if you wanted to build water, you had to build it an atom at a time in a text file with the bond length and the bond angle and all of that stuff. And then you would submit it to Gaussian to do the calculation. But you guys have GausView where you can click and build and spin and look at it and everything like that. So yay, technology. Okay, so this is GausView. It comes up with this little building window here, and you can come up and you can pick all the different elements. If you go there, the carbon tetrahedral right here, this little spot right here, you can pick different types of carbon, or you can go over here and click the periodic table. And so the periodic table that you'll see has all the elements, but when you're picking the basis set and so on, you need to make sure that your basis set covers all the elements. And this figures into your lab too, because later in the semester you're going to do an iodine lab. And we want you to incorporate the Gaussian bond length and vibrational frequency and so on for iodine. And so you're calculating that this week to use in 4 or 5 weeks from now. Okay, but iodine, when I talk about the first 5 rows, let me find my pen. Okay, so the periods on the periodic table, 1, 2, 3, 4. Most of the basis sets stop at krypton, and so even though you can build a molecule with iodine in it, you have to pick a basis set that has the wave functions and everything for the heavier atoms. Okay, and so for iodine, we use LANL2DZ. And that's the Los Alamos National Laboratory, double zeta. Okay, so this is a sort of a way, we'll talk about what the double zeta means. And then for up above here, we're going to use the 6-31G with D in parentheses. So these are basis sets. We'll talk about those in a minute, but while we have the periodic table here, I just wanted to point that group 5 split, where most of the basis sets go to krypton. There's a few basis sets that go beyond krypton, and you have to find those. You can always look at the help. So the help on the software works pretty well. So you can find all the details there. You can also choose what atom type you have right here. So if we're going to pick, say, fully saturated carbon, we'd pick that one. If we wanted sp2 carbon, we'd pick that one. Sp carbon, there's 2 types of that. Okay, or if we just want to stick a carbon atom someplace, we could use that one. If we wanted to do rings, we have this little ring menu over here. So we have the periodic table menu, the ring menu, and we have various R groups too. So we have 3 different menus where we can select things. And so if you click the rings menu, you get all these different rings. And these 2 are really hard to build, by hand. And so it's nice to start with the rings menu. Let's say you're going to make something that maybe like a carbohydrate or whatever. You might want to start with a cyclohexane and then start adding in the OHs and so on and make a carbohydrate. And then you may want to change one of those carbons to an oxygen because it's the sort of the aldol linkage that they make. Okay, so then so in this case we've clicked benzene, this one here, and we end up with benzene. And when we click in this blue field, we get the benzene molecule, which is terribly drawn. Okay. We also could use the R groups. Here's a bunch of different R groups that you have. Okay. And then we're ready to do the calculation setup. So under calculate, no surprise there, we pick Gaussian calculation setup, and then we get this setup window with a bunch of different tabs. We have job type, method, title, and so on. We'll go through those. So on the method, we're going to talk about this today. We're going to talk about these different options that we have here. So on the method tab, we have to pick ground or excited state. All of your calculations are going to be on the ground state. Excited state calculations are pretty tricky. Gaussian's searching for minima, and so when you try to keep a molecule in the maximum with respect to some electronic portion of its electron cloud and minimize all the bond lengths and so on, it a lot of times drops down to the global minimum, and we don't want that. We want it to get stuck in an upper level local minimum for the electron cloud, but then let the bond lengths and angles change. So excited states are pretty tricky. I mean, you have to babysit it. It crashes a lot. So then we have level of theory designation. So this part right here is level of theory. We'll discuss what that means, level of theory, in a minute. And then we have the basis set right here. Okay. So method and level of theory or no, I'm sorry, don't, never mind. So level of theory is right next to the method. And then we have the charge and multiplicity. There's one molecule that you have that's charged Cn minus. And so that would be a -1 there. All of the other ones are neutral, so you'd have a 0 charge. Also, all of your molecules that you're calculating have paired electrons. And so you have a singlet. This multiplicity is the number of unpaired electrons plus 1. Okay, and it comes from the number of peaks that you would see in a spectrum. You remember from NMR, you have all these little doublets and triplets and quartets and so on. Same kind of thing with the hyperfine structure of the electrons. Okay, so paired electrons would give you a single peak. Unpaired electrons would give you 3 peaks, so it'd be a triplet. So it's the number of unpaired electrons plus 1 would give you the number of peaks that you have. And so this is what we have. We have a singlet for unpaired electrons. I mean, for fully paired electrons, we end up with a singlet because there's 0 unpaired electrons plus 1. So model chemistries. This is the theoretical model. And then we also have to select a basis set. And we're going to go through the graphical methods for molecular orbitals, and electron densities, and potential energy surfaces, and then we'll be done. So the reason we can do these calculations in the computer is we're able to separate the nuclear motions from the electronic motions. And that's called the Born-Oppenheimer approximation. So one time I was out playing golf with a friend, and he was frustrated because he's trying to line up his tee shot. And you know how sometimes in the summertime there's a little cloud of gnats? Those gnats were in his face, and he's trying to pay attention to the ball and swing the club, and they're all over him. So he picks his tee up and moves it over here. Well, the gnats followed him because they're so small and so fast. They actually didn't know he was moving. That's the same with the electrons. When the bond is stretching and so on, the electrons react instantaneously to the movement of the nuclei because the nuclei weigh 1,000 times are 1,000 times heavier. A hydrogen is 1,000 times heavier than an electron. So it moves so slow. And so the electrons react instantaneously. This is great because we can pick the location of the nuclei and calculate the electron cloud. And then we can move the nuclei a little bit and calculate the cloud again and see if the energy went down. If it went down, we're getting closer to the geometry that's optimized. So we move the bonds, calculate the cloud, and when we reach a minimum, we're at the geometry that is the lowest energy. And so it's the Born-Oppenheimer approximation that allows us to do that. And so no matter where he moves, the gnats are still all over the place. And so the gnats are the electrons in this case, and then you are the nucleus. So this is the energy equation. So I'm just going to walk through this quickly. You're never going to have to calculate this by hand, thank goodness, okay? But this is it. The Hamiltonian is the total energy operator, so it has kinetic energy and potential energy. So in this case, the T's are kinetic energy, and the V's are potential energy. And we have nuclei, so we have the kinetic energy of the nuclei, we have kinetic energy of the electrons. Okay, and then we have the potential energy of the nuclei. They're both positive, all the nuclei are positive, so they're repelling each other. So there should be a positive turn. It should raise the energy if they get closer. Then you have the nuclei to the electrons, and that's Coulombic attraction. So positive and negative charges attract each other. So that should be a negative term. And then we have the electrons repelling each other. And so that's the positive term. And so here's our Hamiltonian. Looks pretty complicated. Okay. So what I've just said is what we have. We have the second derivative of the wave functions for the nuclei. So let me go through here. So alpha and beta are nuclei, I and J are electrons, M is the isotopic mass, little me is the electron mass, and this del squared upside down delta is just the second derivative operator according to all space. So we did the Hamiltonian by hand of calculating the energy of a particle in a box, but we only had one dimension, so we had x. This has x, y, and z, or if it's like an atom, it's r theta phi in spherical polar coordinates, and so that's what we've got. So these are the second derivative operators. All your wave functions are things that will be returned after taking the second derivative. So they're all cosines, sines, and e to the x's. We also have the permittivity of the vacuum. That's how the charge decreases as you go through space. Okay. And we have R's. All the R's are the pairwise distances. So we have the pairwise distance here between the nuclei. So we just go through a list of nuclei. Nucleus 1 repelled from 2, 3, 4, 5. And then we move to 2, repelled from 3, 4, 5, and so on. So that's what these sums are. And here we have the attractions. The nucleus 1 attracted to electron 1, 2, 3, 4, all the way around. And the nucleus 2 attracted to all the electrons. Okay. And then we have the repulsion of the electrons. So electron 1 repelled from all the others, electron 2 repelled from the remaining set, and so on. And so this term is called electron correlation. So that's a missing letter in your notes. And this term has no solution. And we've come a long way from the particle in a box. This was our Hamiltonian for the particle in a box, okay, for the Schrodinger equation. And now we've got all these particles, we have all these things, but it's the same general function. We now have potential energy because we have charges of particles. The reason the electron correlation term is not computable is because we're treating the electrons like waves, like standing waves, like the slinky, okay? Where along that slinky is the electron? It's not. It's not any position in x. We can square the wave and get the probability of the electron being here or there, but we can't say there's an electron at x equals 3 and the electron at some other place at x equals 5. Now we can calculate the distance between those two particles and calculate that term. We have no location for the electron. We have only a probability of where that electron is. So there's no solution to that term. So we have to do approximations, and that's what we're talking about when we say level of theory. So in Gaussian, we have lots of approximations to that electron correlation term. So since the electron correlation can't be solved, we must approximate it using these different model chemistries, like molecular mechanics. And so I've kind of underlined the ones that I use. This one is a little different in your notes. I thought I changed it. I changed it. So it should be PM6 here now, PM6. And that's the one I use now for semi-empirical. The PM stands for parameterization method 6. And so what does it mean by semi-empirical? Well, we'll get to that in a minute. And then ab initio, that's Latin for from initial, Hartree-Fock. And then we have these perturbation theories that we could use. Configuration interaction, this takes into account excitation of the electrons into different excited states and calculates a better approximation of the ground state by doing that. And then we have density functional theory, and this is the one we're going to use in class, in the lab. So we're going to use this one. It's just a way, we'll talk about it individually, a way to treat the wave functions, really teaching the treating the wave function square, not just the wave function. So molecular mechanics. It ignores all the electrons. And so you don't have an electron correlation term if you don't have any electrons. Okay. Now, how does it get away from this? How does it get away from, how does it get away with this? Well, It takes just the distance between the nuclei. So if you have like water, it calculates the distance to the oxygen and the distance to the hydrogen. And it says there's a certain table of values for hydrogen-oxygen bonded molecules. And we're going to see if it's in that specific distance. And so we're going to have this energy associated with an HO bond. And then we have the hydrogen distance to other hydrogens it's not bonded with. And so we just have a table of distance values with all these different energies. So we have lots of these little equations, but because we're not calculating the electron correlation term or any of that stuff, it's a very fast calculation method. And so it just says every pair of atoms, whether they're bonded to each other or not bonded to each other, has a minimum that they would like. And this epsilon is this distance here. Look at this. And there's one of these potentials for every pair of atoms in the molecule. Incredibly fast. So you would just pick mechanics in this level of theory here, pick mechanics, and then you could go down. I use UFF. It's universal force field. So it has every atom in the periodic table and then a whole bunch of different bonding interactions that it has. Semi-empirical methods. Well, this eliminates the core electrons. So that's pretty nice. If you look at the periodic table, what are the valence electrons? If you go from lithium, it has 1 valence electron. You get all the way over to fluorine, it has 7 valence electrons. You get to neon, it's 8. And then you go to the next row, sodium has 11 electrons. So if I'm treating every electron in sodium individually, I have to calculate 11 of those terms, the attraction term, the repulsion terms, and so on. But if I'm getting rid of the core electrons, I only have 1 electron in sodium. So sodium will take just as long as lithium and just as long as hydrogen. So it really speeds things up. If I get all the way over to chlorine, I'm at 17 electrons. Again, that would really slow things down. But if I get rid of the core electrons, I only have 7 electrons, and it goes really fast. It costs the same as using a fluorine. Same with a really huge atom like iodine. Still only 7 valence electrons. So it can be calculated just as fast as a fluorine. So semi-empirical methods are really good. Now, how do they get rid of the core electrons? Well, they look at how the core electrons shield the nucleus. And so they would treat the nuclear charge on carbon different than the charge on silicon. So they wouldn't say that the nucleus on silicon is charged 14 positives. They would say that the core electrons have reduced that down to maybe 10, maybe 4. So they've shielded maybe 10 of those nuclear charges by the core electrons, and now those 4 valence electrons are attracted to something that has 4 charges on it. And so then that's how they get away with treating silicon differently than carbon, but still only having 4 valence electrons. And so this changes the different nuclear charges. This is essentially what I just said. It's great for atom types that don't break the rules. So what's a type of atom that does break the rules? Well, something that's really strained, like cyclopropane. Did y'all do cyclopropane on the group theory day in lab? No? It's a good one. Okay. What do you think it is? It's D3H, right? You see it? D3H? Okay. So this carbon has 4 electron domains around it. Okay. Do you see that? 4 electron domains? So it is sp what? 4 electron domains. Yeah, so sp3. I've got my 4 here. I want to join the 3 to stick the p's together. So I got sp3. Okay. If I had 3 electron domains, it's sp2. Okay. sp if I just have 2. So 4, I've got sp3. I don't know if I showed y'all that trick before. So this is sp3. And then what are the angles that it should be between all the different bonding things? 109.5, okay. But what is this angle right here? What's this angle on the inside of an equilateral triangle? 60. Yeah, that's breaking the rules, isn't it? 60 degrees. So that's a strained ring. and it's not going to like, it's going to be at a higher energy. So the semi-empirical method would have a hard time with this molecule because it's going to say, oh, I got an sp3 carbon. I'm going to want my angles to be at 109.5, and this molecule, in order to stay together, is going to need those angles to be 60. Now the others can make up for that. They can be further apart and so on. So to do the semi-empirical, oh gosh, my eraser is gone. I'm making it worse. All right, so anyway, pick semi-empirical, and then you come over here, and I said PM6, that's the one I like. Okay. Then ab initio and density functional theory. So this one, you have to have two parts. You have to have the level of theory and a basis set. For mechanics and semi-empirical, they have their own basis sets. You don't have to fool with that. And they cover all the atoms. But for these more, I say, mathematically rigorous models, you have to pick a level of theory, and then you have to pick the number of functions you're going to give to the electrons. So the more freedom you give the electrons, the lower the energy. So this is our theory for estimating that electron correlation term. Hartree-Fock methods ignore electron correlation totally. They just leave it off. And you think, well, that's kind of crazy. It's going to be totally inaccurate, but if you're doing like reactants and products, and you're taking the, products minus reactants and so on, the error in the products and the error in the reactants is going to be similar, we hope. And so, yes, we're losing something from our calculation, but we're losing it from both sides of the reaction. And so it's not too bad. So it could be worse if you're just picking that energy of a molecule. But most of the time for these calculations, you're doing comparisons. And so if you're comparing two things and you're neglecting the one thing from both of them, then you still get a good comparison. These other methods just try to correct that, ignoring the electron correlation in different ways. So then we end up with density functional methods. So here we would pick in our theory section, we would pick DFT, and then we would come over here to this drop down, and this is the one we're going to use in lab, B3LYP. And then the basis set, we need to talk about what these basis sets are. So this density functional theory is treating the total electron density as instead of just the individual wave function approach. We need a basis set for building up those electron wave functions, though. And so here's how we would build that basis set. So here's all the different options. We come down here to 6-31G. So we pick that one. Okay, we have some options. This STO3G, Slater type orbitals, this is the minimal basis set. So this has what you would typically pick on a periodic table for your electron correlations. So hydrogen, its valence electron is in a 1s orbital. Okay, we're talking about ground state electron configurations. Carbon has a 1s, it has a 2s, and it has 3 2p orbitals. And so that's it. That's all you get for the Slater type orbitals. And so on. Chlorine, you've got then the 3s added on, and you got the 3p's as well. Split valence set has a bunch of different Gaussians. So let's talk about where this name of this program came from. Okay. The wave function, the radial wave function for hydrogenic orbitals is an e to the minus r. It looks like this blue curve here. So this is distance from the nucleus. And like I said, if you square the wave function, you get the probability distribution. So this makes it look like the wave function for an electron is most probable to be in the nucleus. But what happens when you try to integrate that area under that curve? This is a radial wave function, and so you're trying to integrate the volume element as it goes to the nucleus, and the volume element as it goes to the nucleus goes to 0. Okay, so it's an r squared term, and so when you integrate to 0, the wave function looks like this. You put in that volume element. Now, e to the minus r integrals with the volume element take a lot more time computationally than Gaussian integrals. Okay. And so Gaussian integrals just have, you can just look up the integral values for those. And so what they do is they try to approximate the e to the minus r wave function using e to the minus r squared functions, Gaussian functions. And so that's where the software got its name. So they'll have like a fat Gaussian to catch this region, and then they'll have a bunch of smaller Gaussians that are really sharp to try to catch this region, and so on. And so we have primitives, which are the ones that try to capture the main part of the wave function, and then you can add in more contracted Gaussians, and it's actually faster computationally to have, say, 6 or 7 Gaussian functions modeling one single e to the minus r than try to calculate the integrals of the e to the minus r functions. So that's where Gaussian came from. That's why it has its name. Now, the principle is the more functions you throw at the electrons, the more freedom they have. And what do they have in nature? There is no electron that says, I really want to go over there, but I'm stuck in this cosine function. The electrons don't know anything about trig. They just go wherever the charges are. Okay, so if they want to be halfway between two nuclei, even though the Gaussian curve says they should really drop off, the electron's going to want to move further out because there's more positive charge out there. So the more freedom we give the electron, the more like nature it is, the more accurate it is. Okay, but that costs us computational time. So that's where we run into trouble. And so we have all of these choices. So these are, in this parentheses region, we have our basis set, the like base level 6-31G. Then we can add in different higher orbitals, like d orbitals, to things like if we had a carbon or a nitrogen, those things don't have any electrons in a d orbital. But if I add a d orbital in my computational method, then my electron would have the freedom to go at angles other than 90 degrees. Like, where are my p orbitals? P orbitals go along the Cartesian axes. If I want to go diagonal, I need some d orbital character. Okay, and so I could maybe pick a d there. And so that's what we will do. We'll do 6-31G with a d in parentheses. And so we're adding d orbitals to all of the elements other than hydrogen. Okay, and that's one thing. A lot of molecules have lots of hydrogen. And so if I'm adding d orbitals to hydrogen and they never want to use them, they don't care about them, I'm just wasting computational time. So we split the hydrogens and everything else. So we can save a lot of computational time by treating hydrogens differently. Now, if we have something that wants to hydrogen bond, we might put a p orbital on hydrogen. And so it'll put a p orbital on all the hydrogens, and then the hydrogen has some directionality to the way it can bond. So again, more freedom for the electrons allows us to get odd angles and better hydrogen bonding and things like that. What if we want the electron cloud to expand? Like, say maybe we have a negatively charged molecule where now the electron cloud is negative and it wants to expand because the electrons hate each other. They want to get farther away from each other. We can add more s orbitals to our atoms and let them go further out into space, and that's what these pluses are. So 1 plus will give an extra s orbital to all of the atoms other than hydrogen. If I do 2 of those, I get s orbitals, extra s orbitals on all of the atoms. When I say, I'm not specifying which s orbital, because for, say, chlorine, I'd be adding a 4s orbital. If it was fluorine, I'd be adding a 3s orbital. So it's just adding those diffuse functions, allowing them to get further, the electron to get further from the nucleus. Those are good for transition states and anions. So this is a monster basis set for really good energies. We have an extra 1 here. We have the 2 diffuse functions on hydrogen and everything else. We have d and f orbitals on top of all the heavy atoms, the ones that are not hydrogen, and we have p and d orbitals on the hydrogens. So this electron has a lot of freedom to go in any direction it wants. So let's wrap all of this up. If I have a huge system, I'm going to want to go molecular mechanics or maybe semi-empirical. If I have anions, I want diffuse functions here. If I have transition states or maybe strained rings. I need some more of these polarization functions to give it more direction in space. This book, Forsman's Electronic Structure Methods Using Gaussian, he suggests this. Our computers are fast enough now, they can handle sort of a baseline calculation like this. And he likes this APFD, but I've been doing everything with your lab with B3OIP, so it's been the industry standard for 20 years or so. So we're just sticking with B3OIP. But anyway, our computers are getting fast enough, we can add a little extra rigor to our calculations. So this is just review. I want to get to playing with the software. That's why I'm going to go through this quickly. So this level of theory plus a basis set is called a model chemistry. Now think about your model chemistry sets, like if you build a molecule. And let's say I built a molecule using a set from one vendor, and you built a molecule with a set from a different vendor. And I show you how long my carbon-hydrogen bond is, and you say, nuh-uh, it's this long. That's a stupid comparison, isn't it? Because I have a kit from manufacturer 1 and you have a kit from manufacturer 2. Our bond lengths should not be the same. Same with this. Our level of theory and basis set is a different manufacturer. So I can't do a calculation with molecular mechanics and say this is my CH bond length, and you do a calculation with Hartree-Fock theory and say this is my bond length, and let's get into an argument. We can't compare those two because they have different model chemistries. So the model chemistry is like the model set that you use. It has its own set of, it's going to generate its own set of bond lengths, angles, and so on. Now they're not going to be drastically different, but I mean 0.1 angstrom is a big difference. So you may think, oh, it's 1.12 and mine is 1.22. That's a huge difference in bond length. Okay. So this is sort of a diagram of what I'm talking about. If we wanted to give our electrons complete freedom, okay, it would take a long time, okay? But we could do it as long as we kept the level of theory low, like molecular mechanics and so on. If we wanted to do our complete electron correlation over there, we could have a huge level of theory and really, get into the fine details of how the electrons are interacting with each other, but we'd have to do that with a really small basis set, or we would run out of time. Our calculation wouldn't ever end. Okay, so if we come down here, this calculation time goes to infinity as we try to get a complete freedom in our electrons and to calculate electron correlation accurately. I've had calculations. I think my longest one is two weeks, a little over 2 weeks of CPU time. So the computer was calculating for 2 weeks. It was a PC, but still, it was chugging along. So for your job types, we're going to do opt and freq. So it's an optimization and a frequency calculation. And it does both. It optimizes the structure and it calculates the vibrational frequencies. Now, sometimes this little button doesn't say yes, and you need to make sure it says yes so that you calculate the Raman intensities as well. Okay? So come and make sure this says yes. Do opt and freq and make sure it computes the Raman. Then we have the title tab. That's where you put your name in and whatever lab you're doing or whatever, 4448 or whatever it is you want to put in the title section. It's totally up to you, but I would avoid using these special characters because these characters are used elsewhere in the output file. And then we have this link 0 tab. Now you don't really have to do anything with this tab, but this is where your checkpoint file name goes. And now they've made it so nice that it takes the parent file name and puts .chk on it. You used to have to fiddle with that, now you don't. So Gaussian's improved. Let's talk about computational time. So there's a molecule, triamino trinitrobenzene. It's a nice calculation because it has 300, when you do this, it has 300 basis functions. And I was able to find this information right here. I think this is, no, this is it. So I found this article that said TATB took 9 minutes on a Cray supercomputer and using Gaussian 92, and Gaussian 88 calculating the same molecule took 1 hour. So back in 1980, a VAX supercomputer took 1 week. And then the polyatom, the very first version of Gaussian, written in 1967 on a CDC 1604 mainframe computer, took more than several months. Okay, so then I had all of this data from the past, and so these are all the computers that I calculated it on, all the way up to Gaussian 03. I need to do it up there in the lab and see what 16 will give me. But this was my smoking computer, man. It had a 486 and this 50 megahertz CPU. Now they're in the gigahertz, so that's pretty silly. But it took 20 hours to do this calculation. Then I got a Pentium 90 and it took 2.6 hours. And then I got a Pentium 3 500 megahertz and it took 24 minutes. And then now we're at the Pentium 5 3 gigahertz machine. It took less than 5 minutes. Then I told you in that summertime I had a job that took over 2 weeks. And so if I take this slope of this over time, how long would that job take in 1967? 1,500 years. So that's like it breaks my brain. Kind of like a Doctor Who episode, right? So, in 1967, he's like, we got to calculate the geometry of this molecule, and it's going to take us 1,500 years. We don't have that time, okay? So we're going to get in the TARDIS, and we're going to jump ahead to, 2003, and we'll calculate it in 2 weeks. So, yeah, that's sort of what the advancements in computational chemistry will do for you. So we've advanced the software and the hardware. These machines were millions of dollars, and now we're doing them on laptops. It's crazy. So this is what Gaussian does. We input the nuclear coordinates. We calculate the energy. So what is that, the energy? It's the electron cloud energy. So, and of course, it takes into account the repulsion of the nuclei, but then also the attraction of the electrons. And it's the electrons that hold the molecule together. If you were to get rid of the electrons, all the bonds would blow apart because they're all the positive nuclei. Okay, then this gradient, that's the slope of the electron cloud. Does it want to move somewhere else? What's the energy with respect to the nuclear positions? And so are we at a minimum? We can answer that question, yes or no. So Gaussian will check to see, are we at a minimum here? If no, then move the atoms. So if I'm too close to this atom next to me, and it calculates the gradient, which is the slope, and it says, your energy would go down if you move that way. So then this changed geometry moves me a step that way, and then starts over to calculate the energy, calculate the slope. Now I've gone too far, and the slope is this way, and saying, you can get a little bit closer to that atom again. Let's move, and we'll find the right spot in distance to that atom. And it's the electron cloud that's overcoming our repulsion. So once we find the electron structure, we have the geometry. So if we're at a minimum, then we do a frequency calculation. So it's actually two calculations, an optimization and a frequency calculation. Do the frequency calculation. There are such things as global minima and local minima. So let's say, I don't really want to stand on the stool, but I think I will. Okay. So the slope at the top of this stool is 0, okay? Because it's a critical point. And so, but my frequency, if I go to the right or the left, the parabola goes down. So where's my vibrational frequency in that parabola that's going down? It's actually negative. It's below where I'm at. If it was a regular harmonic oscillator, the potential energy would go up and my frequency would be positive. So if I'm in a well, my frequencies are positive. If I'm on top of a hill, my gradient is still 0, but my frequencies are negative. And so that's finding like a transition state where your atom is not in a stable position. It's actually it may be negative in all other areas. Think of a Pringle. The steep side that go up, you're at a minimum with respect to that, but you're also at a maximum with respect to going down the waist of the Pringle. So if you have negative frequencies, you're not at a global minimum. And so we go up, we reduce the symmetry, because typically it's the symmetry of the molecule that causes that to happen. We move the atoms around, we kick the atoms off the top of the stool, that involves changing the geometry, and then start again, redo the optimization. When we find ourselves at a minimum, we get over here at negative frequencies. If there's no negative frequencies, then we can be fairly comforted that we're at a global minimum. You never can guarantee, like right now I'm doing cannabinoids. These molecules are huge. There's no way that I'm going to say I'm at the global minimum, because this floppy thing over here could be here or there, and I've got all these dihedral angles. There's no way for me to know without an enormous number of tedious calculations whether I'm at the global minimum. Okay, then the output file is a .log file. If we're going to simulate spectra, that's a typo, just scratch through the US if you have that on your notes. If we want to simulate the spectra, the IR and Raman frequencies and intensities are in the .log file. If we were to do an NMR calculation or a UV-Vis calculation, those would also be in the .log file. If we're going to look at molecular orbitals or electron density surfaces, electron cloud, these would be in the checkpoint file. Okay, so there's electrostatic potential maps too. Let's look at all of these things. So this is a picture of a molecular orbital. Is that in your notes? I see a lot of page flipping. Yeah, there we are. Okay. So if we're looking at molecular orbitals, this is where we would get them. We would get them out of the checkpoint file. We're not doing that for the lab, but if you wanted to look that up, you'd load the checkpoint file, and then up there's going to be a thing called the MO editor. And you can Google how to play with that. But you can get these really fantastic molecular orbitals. So that's where all the ones come from that I show in class. This is actually cool. This is a picture of the electron cloud out to like 95%. Okay. So on the left here, I have that as an ISO value of 0.01. So that's the 99% surface for the electron cloud. So 99% chance of finding the electron inside that surface. Okay. What if I made it 0.05? This is the 95% surface. So if I made it 0.1, it'd be even smaller. So 90% would be closer. So if we wanted to go to 100%, it would just be out to infinity. Okay, so we don't want to do that. But 0.01, so 99% surface is a good one to choose. Okay. It looks a lot like the space filling model. Have y'all seen space filling models? Did you see those in organic? Yeah. So the space filling model is really pretty good. It looks very much like the 0.05 or the 0.01 electron density surface. So a space filling model is a 95 to 99% electron cloud surface. Now we can learn something from the total electron density. Like let's look at HF. And where are the electrons in HF? So here's F, here's H. Look at the shape of the electron cloud. Does it make sense to you? It's mostly the fluorine, and you got a little hydrogen stuck on the side. Look at lithium hydride. That's weird, isn't it? Why is it hydride, I-D-E, just like fluoride? It's an anion. Hydrogen's acting like an anion when compared to lithium. So that's pretty neat. And Gaussian can give us those kinds of comparisons. Now we could also color this. Let's say we walked around this map. Let me draw my little person walking around. Okay. And he's got in his little hand, we're doing this mathematically, he's got in his hand a little positive charge. Okay. Now what do we mean by walk around? Well, we just use math to put a positive charge every place on this surface and measure how it's attracted or repulsed from the molecule. So if we're over here, we have a positive charge, it's going to be attracted to the fluorine because this side of the molecule is negative. And if we're over here, it's going to be repulsed by the hydrogen nucleus, so this side would be positive. So if we map out the electrostatic potential by walking that positive charge around, then we can get this electrostatic potential map. So this is benzene, and if we walked around that electron density surface, out here by the hydrogens, we would see that it's positive. Up above the delocalized electron ring, we see that it's negative. So if I'm coming in as in organic chemistry and I've got a nucleophile, so I've got a negative bromine and it's coming at this molecule, what is it going to attack? It's going to attack the positive parts of the molecule, okay, for a nucleophile. So it's going to find those positive areas and that's where it's going to hit. What if it's an electrophile, okay? Then it's going to go where the electron cloud is. And I've always thought it would be great to have a student go through PChem after Gen Chem 2 and then go into organic, because they would know about molecular orbitals, they would know about things like electrostatic potential, and electrophile and nucleophile would totally make more sense if they could have these visual representations. But they won't let me like experiment with you guys on your curriculum. Anyway, so it'd be fun. It makes them really good organic chemists is what I think it would happen, because they would get through PChem and not quite understand it, and then they get into organic chemistry and it would click and they're like, oh, I know chemistry like the back of my hand now. And so I wish they'd let me. Okay, so here's benzoic acid. Sure enough, here's that acidic proton, very, very positive, okay, ready to be donated to a water molecule or whatever. And you got the negative oxygens. They're not very negative because that negative charge was delocalized over the whole ring, okay, and that's what stabilizes the anion. Now we can do funny things in computational chemistry that we could never do experimentally, like rotate groups and see what happens to the experimentation, or to the cloud. So here we've rotated this this carbonium anion this way, and we see that the ring has become more red. So this is just showing that electron density flows out onto that group when it's planar, and when it's not planar, it can't delocalize. So there's just some other examples here where our particle in a box, the potential energy was 0 except at the barriers when it went up to infinity. But we can actually calculate potential energy surfaces using Gaussian. So you can take the molecule and rotate a certain angle and calculate the energy at multiple places. Last few things, we can do transition states. And then these are just showing you experiment and calculations, and it's pretty good on bond lengths. These are our errors. And it's okay in vibrational frequency. So these are the percentages. Some are pretty far off at 33%, and some are really good at 0.4% error. So have fun this week with Gaussian, and enjoy building your molecules. And if you want to just play around and build some other kind of crazy molecule, if you want to, that one we did acetophenone in the lab, which we typically draw planar, but you'll see if you try to build it, it can't be planar. You got a ketone in the middle and 2 phenyl rings, and those hydrogens bang into each other. So that would be a fun one to build, just for fun.